Okay, this is going to be our first video in our current resistance and electromotive force series. And so in the past, I guess 4 chapters, we've been studying interactions of electric charges at rest, right? So all the situations we've looked at, these charges have been at rest. We now want to look at situations where the charges are in motion, okay? So when an electric charge is in motion from one region to another, we say that there's an electric current, okay? And if that current flows through a closed loop, like a loop of wire or something, we say that this is an electric circuit, okay? Electric currents are going to allow us to transfer energy from one place to another. So, for example, we could transfer energy, electric potential energy from a battery to a light bulb or a fan or something else like that. Okay, so we're going to start our discussion here by talking about current, and everything I'm talking about here is from chapter 25 of the text. This first video is going to be focused on on section 25.1. And so let's get right into it. A current is any motion of charge from one region to another. The current that we're going to run into most often will be current running down a wire, right? There can be current in other things, solutions, different types of things, but we're going to mostly, when we're thinking about current, we're going to be thinking about wires and batteries and different circuits that we could make, right? So okay, so in all of the electrostatic situations that we looked at previously, our electric field was zero everywhere in the conductor, right? So there was no current flowing, and we said there could be no electric field in a conductor which was in equilibrium, which was electrostatic, right? We saw that these charges that are in the conductors can rearrange themselves along the surfaces. So maybe I'll take a second to draw a little picture here. So we know that there are currents, not currents, that there are charges in these conductors, even in an electrostatic situation, right? Remember, in the chapter on Gauss's law, we talked about how if we had a conducting hollow sphere, let's say it was something like this, initially, if there was no net charge on the sphere, the charge would be nowhere, right? But there is still charge sitting inside there. There's just no net charge. There's free electrons free to move. And as we dumped, let's say we dumped some sort of a positive charge into the center of our hollow sphere, remember we had a bunch of negative charge piling up here, which ended up giving us a bunch of positive charge building up along the outside. So where are these charges sort of coming from? Like these charges in the hollow sphere weren't there before. Well, they kind of were there before, right? There was just no net charge, and now they're sort of spreading themselves out in such a way that they're giving us no electric field inside the conductor here. But there was free charge. It just wasn't free net charge inside our conductor there. Okay, so now we're going to take a look at how these free charges that are free to move inside our conductor are going to arrange themselves as we force an electric field through this conductor. And let me just double check something. My other monitor just went blank. Give me one sec. Okay, so we've seen, so as I was saying, we've seen that there are free charges in these conductors, and in general. So what's happening? Let's say we go back to our hollow sphere here. We're going to take the positive charge out of the center of it to clean the diagram up a little bit, so there's no charge kind of anywhere. But what's actually happening here, and they have a nice diagram of this on the next page that I'll show you guys, but I'll draw it here first. There really is some charge, but it's kind of all moving randomly, and there's no net charge. So inside here there are free electrons. Let's say this is some chunk of conducting material, maybe copper, maybe aluminum. There's a lot of free charge that are zipping around in here, and they're moving around quite quickly. They're moving around with speed somewhere around a million meters per second, right? And they're all just zooming around in here in random directions, but not in any one particular direction, right? And it's not a net charge. It's just that some of these free electrons, well, that some of these electrons are free, so they're able to move around in here. So now we're gonna look at a situation where we're not dealing with a hollow sphere like this, but we're maybe dealing with a wire. And what we're going to do is we're going to do what we couldn't do in the case of electrostatics. We're going to see what happens if we introduce a constant electric field, if we sort of force an electric field to be established inside the conductor, and the charged particles. Well, we're going to see what happens to those charged particles. The charged particles are going to experience a force that we can see here. So the electric force, all these charged particles will experience this force because we're going to have set up this electric field. And if it was the case that these charged particles were sort of just sitting out in the open in the vacuum, let's say, they would start to accelerate to a fairly high speed fairly quickly, right? But inside this conducting material, this stuff is actually made up of a bunch of matter, right? So there's constantly a bunch of collisions happening, and the direction of these particles that are whipping around are changing. And so we're going to see that what we actually set up, instead of a single particle moving at high speed down our conductor, we're going to see that really what we start doing is having all this collection, this jumble of free electrons drifting slowly down the wire. And so I'm going to stop trying to draw this poorly as I'm doing here, and what we can see instead is this nice diagram that they have set up for us here. I think this is figure 25.1 from the text. So we can kind of see what they have set up for us here. Imagine that P1 here, this is our free electron or any free particle in our conducting material. It would have to be charged, right? And so generally speaking, this would be a free particle, or at least for what we're talking about here in this section, this would be a free particle, and normally it would whiz around following, let's say, the blue path. Okay, but if we introduce an electric field, like we force an electric field into this conductor, then what happens? Well, slowly but surely, the particle would normally be following this blue path, right? But slowly but surely, we're going to push it a little bit further down to the right. Let's say our electric field is pointing in this direction here, and we have a positive charge. Then what's going to end up happening is we're going to end up having a slow drift to the right. This particle will still be bouncing around a whole bunch, but as it's bouncing around off of things, it'll be slowly being moved to the right, and this is going to be happening to all the free particles, all these free electrons that are in our conductor. So what we really have is a drift velocity, all this sort of column of free particles. You can imagine that this wire is just a column of free particles. There's a bunch of particles zipping around in every direction in here, and the whole column is slowly moving down in this direction of our electric field, assuming that they were positive charges, right? And now it kind of matters if they're positive or negative charges and the direction of our electric field if we're talking about the individual movement of these particles. But in the end, we're going to see that the direction doesn't really matter when we're talking about currents, okay? So when we're talking about charge moving in a wire and we're talking about current, we kind of want to have these two different pictures in mind. We want to think about the individual charges, the individual particles moving around super fast, but bouncing around kind of randomly, but their overall sort of motion is gently pushed in the direction that our electric field is dictating, and the whole sort of sea of them is moving down with a much slower drift velocity than any one of these particles would be experiencing, right? So we see here, down here, I note that the drift velocity in a lot of these materials would be somewhere on the order of 1/10 of a millimeter per second, where we remember that each of these individual electrons is moving along at about 1,000,000 meters per second, right? So the electrons individually are moving very quickly, but most of their motion is random. But overall, we have a total drift velocity of this whole sea of free electrons moving at about 10 to the minus 4 meters per second. Okay, and so this is kind of the picture we want to have in mind. But we also want to think about this in terms of the whole sea of electrons, right? So you have this whole collection. Maybe I'll make an attempt at drawing this here. You can imagine this is our wire here. We have this whole sea of free electrons here, and each of them has this high velocity, crazy bouncing around going on. And there's also this electric field. Let's say we have an electric field set up in this direction inside the wire. And so it's slowly moving the whole column to the right. But the electric field sets up very, very quickly. Let's say we force the electric field into the wire. It'll set up over the entire wire very close to the speed of light. And so what happens is the whole column of all these electrons start to move in this direction basically instantaneously, not quite instantaneously, but simultaneously. They all start moving in that direction as a huge column. So as we set up this electric field, we right away have electrons, and obviously this isn't a closed circuit, but imagine that it was. You would have electrons pouring out of this end, right, and into the rest of our circuit, which would go wherever, right? So right away, as you set up the electric field, we have a flow of current through this end piece, through this piece of cross-sectional area, because our electric field is set up instantaneously. And so we have these sort of three things going on. We have the electrons having their own individual motion. We have this overall drift velocity of all the electrons, and then we have the whole thing moving as one solid column almost. So you can imagine right away as you hit the switch and the electric field is set up, all the electrons start moving. So instantly you have, so let's say you turn on your light switch in your room or whatever. It's true that the drift velocity of all of these electrons is only going to be moving at about 10 to the minus 4 meters per second. So it would take a long time at a tenth of a millimeter per second for the electrons that just pass through the switch on your wall to make it all the way to your light bulb, right? It would take, several minutes for it to get all the way up there. But the whole column of electrons which exist in that whole wire between your switch and your light bulb starts moving basically simultaneously as soon as you hit that switch. And because that's the case, you see the lights go on right away, right? So think about these three different types of motion that are happening here, and this is kind of what we want to have in mind as we think about current down a wire. Okay. And so let's talk about the direction of current flow here. So the drift of these moving charges through the conductor can be thought of in terms of work and energy as well, right? So we can think of the electric field doing work on the moving charges. Okay, the charges can either be positive or negative, depending on the type of conductor we're using. When we're talking about wire, like when we're talking about wires and we have electrons moving down the wire, they're going to be negative charges moving down the wire. But we're not concerned about that so much. We define the current, I, which we're going to give this symbol I here, so that's going to be our symbol for current, to be the direction in which there's a flow of positive charge, right? So we're always going to think of positive charge as moving in the direction of our current, right? And maybe did I have that image here? I don't. I have it below. Okay, so I'm going to show you an image below. But we're going to have our current moving in the direction of the flow of positive charge. So even if you have negative charges moving in the opposite direction, you're still going to have a current. So maybe this is better explained with the diagrams. You can see here that we have positive charge moving to the right, an electric field set up in the conductor to the right. And so because the positive charges are moving to the right, we say that our current is to the right. But this is the same functionally to us as saying that, well, we have a bunch of negative current or negative charge moving to the left. We can see our electric field set up in the wire here again, so our negative charge is going to move to the left. This is again producing a current to the right because it's negative charge moving left, so it means current moving right. And so both of these are going to have the same current to us. We don't really care if it's positive charges moving to the right or negative charges moving to the left. We're going to have a current going in this direction down the wire, given by I down here. Okay, and so this whole sort of discussion of positive charge moving, this is what we call conventional current. When we talk about conventional current, we're thinking about positive charge moving down a wire, even though if we know actually functionally what's happening is negative electrons moving in the opposite direction, right? But we just want to think about positive charge moving down the wire, okay? And so maybe I'll go back to the diagram here. We can see that that's what's happening here, and we have another, excuse me, We have another example here of our current. This is sort of just a blown up section of the wire. We can see we have a battery here, positive terminal here, negative terminal here. And so we can imagine positive charges coming out of the positive terminal, running down the wire, running through this section where we're looking at it, and running up into the light bulb, and giving off some light, and then back down into the negative terminal of our battery. But we could just as easily think about this as negative charges leaving the negative terminal of the battery, going into the light bulb, flowing back through here. We'd have the same current, right? Because we have the same direction of electric field. We could imagine these were negative currents or negative charges going that way, and so we would still have the same direction of current because they're negative flowing in the opposite direction. So the two minus signs kind of cancel, and we would end up with the same sort of picture, right? Okay, so let's try to keep this sort of this image on this page, and we can see that in this last image on this last page, we can see that I flows as the positive charge would flow, right? Like the positive charge would flow out of the positive terminal through our chunk of wire here, where we have the sort of blown up look of it. We have our electric field set up. We have our positive charges going through to the right here, right? And so we can see that it would flow sort of in the direction indicated there, and we define the current through a cross-sectional area, and our cross-sectional area is going to be this disk here, right? We can see this is our A. So our current's going to be defined as the current through this area A, which is really the net charge flowing through that area per unit time. So this boxed equation is an important one to remember. This is going to be our current is equal to the time rate of change of our Q, our charge through that cross-sectional area. Okay. Note that we don't define current as a vector here. When we're talking about current here, we want to be thinking of current always flowing along our wire, and just being the magnitude of the current going in the sort of direction of the wire, right? You can imagine a very bendy wire. It would be very difficult to start talking about a single vector that would describe the flow of that current. So we talk about it in terms of a scalar, and its direction is simply down the wire. Okay. Okay. And so current comes with SI units of amperes, or often just called amps, and 1 amp is 1 coulomb per second. So when we say 1 amp of current, well, that means that we have 1 coulomb per second of charge going through this cross-sectional area. Okay. And so that's our definition for current. Let's now take a look at current and drift velocity, which we've already talked about before, and we're going to sort of derive this expression for current density built out of those two earlier definitions, current and drift velocity. So remember, current we just talked about here. Drift velocity was that velocity of the electrons, the sort of soup of electrons moving down, this sort of whole collection of electrons moving down the wire, right? So that's our drift velocity. Okay, so we want to derive this expression for current density, which we're going to call J. And so again, returning to the image that we see over here. Unfortunately, I can't have it on screen while I talk about this. But so if we return to that image, we want to assume. Let's start off by assuming that there are n moving particles per unit volume of this chunk of stuff, right? So we have some wire, and in that wire we're going to have n concentration of particles that are able to move. We call n the concentration, or the concentration of particles. We're then going to assume that all these particles move with the same drift velocity, so we have this overall Vd, right? And this is a good assumption because we know that all the charged particles in this setup at least move with a single drift velocity, so the whole thing is going to be moving like one sort of column through the entire wire, right? So then in a time dt, so in some infinitesimally small time, each particle is going to move some very small Vd dt, right? It's going to move some time times the velocity. It's going to move that distance, right? And so the volume of the cylinder traced out by all of this moving charge over a time dt through this area A here, right? So there's going to be some cylinder sort of traced out, like there's a little thickness to this cylinder here, traced out over the time dt that this thing is moving. We're gonna end up with a volume for that cylinder that's traced out of A Vd dt, right? So there's going to be some. Remember, this portion of this expression here is just the distance that each particle is going to move, and each particle is going to move over some. Well, a bunch of particles will move through that area that we have defined, right? So this is going to trace out basically a cylinder, and this is going to be the volume of that cylinder. Okay. The number of particles in that cylinder is simply going to be the volume of that cylinder times the number of charges per unit volume, which is the n that we set up before, right? So we end up with this expression here, which is the number of charges per unit volume times the volume, right? The volume of our cylinder. Okay. Then if each particle is carrying some charge q, we can then define this dq, which is going to be the total sort of charge flowing through that area in a time dt, given by the expression here. Basically, we're just taking this previous expression here and hitting it with a q. So our dq, the charge that flows through that cross-sectional area, is going to be equal to the charge on each charge times the number of charges per unit area per unit volume times the volume of the cylinder that goes through that area in the time dt, right? And if we rearrange this, we're just going to move the dt over to here in the basement. Well, that just gives us back our current, right? And so we know our definition for current is the time rate of change of our charge flowing through that area, and this gives us another way to write our current, right? And now we can finally, as we wanted to at the beginning of this paragraph here, we can now finally define our current per unit cross-sectional area, which is called our current density, and we give it the symbol J, and it's going to be defined as our current over the cross-sectional area through which that current is flowing. Okay, and we have this definition for it here. What are we doing? We're just basically dividing I by A, so the A kind of gets pulled out of it, and I've rearranged some of these variables here. So we have NQ VD here. Okay. This current density comes with units of amperes per square meter. Okay, and we want I and J, so we want our current and our current density to be independent of the sign of the charge that we're using. So we're going to take the absolute value of these magnitudes. Okay, and it's going to give us these two expressions that we see here. Now why do we want them to be free of signs? Well, we want it to be free of signs because we're not talking about the sort of direction of these, right? We talked about how these aren't vectors already, although we're gonna discuss what the vector version of our current density could be. But written in this way, they're both scalars. We want no sign on the charge, and so we take the absolute value of those charges. Okay, and now we write it down in vector form here. If we're interested in the vector form of our current density, well, we just take the vector expression for our drift velocity, right? And so those are sort of the three of the main takeaway equations, or really the three main takeaway equations from this section. This equation number 1 here is really just restated in equation 5 here. So these are the three equations you want to be using, and they'll probably be added to the formula sheet here shortly. So those are the sort of three equations we generated. Let's now take a look at a quick example of how we might use these, and this one example will sort of finish up the video for us here, and we'll move on to the next one here. So what do we have here? This is example 25.1 from the text. Current density and drift velocity in a wire. We have an 18 gauge copper wire. This is the usual sort of thickness of wire used for lamp cords and so forth, a lot of appliances around the house. It has a diameter, so not a radius, but a diameter of 1.02 millimeters. it carries a constant current of 1.67 amps to a 200-watt lamp. Excuse me, the free electron density sorry, the free electron density in the wire is 8.5 times 10 to the 28 per cubic meter, so that's how many free electrons we would expect to find in 1 cubic meter of this stuff. And we want to find in part A the current density, and in part B the drift speed, or the magnitude of the drift velocity, right? So in part A here, we're going to start off. Well, so what do we want? We want the current density, okay? And we know that one definition for our current density is we can write it like this. And we're given I. We're told what the current is. So really, we're only left to have to find A, and then we can probably get at our J pretty easily, right? So our A is just going to be the cross-sectional area of our section of wire. Well, our wire, we can assume is like a cylinder, so it's going to have some sort of circular cross-section. It's going to have an area pi r squared. Well, we're not given r, we're given d, so we know that this is just going to end up being pi d over 2, which is an r squared. Well, this we can just rewrite as pi d squared over 4, let's say, right? And so we can just substitute in numbers at this point. This is going to give us our area, which is going to be something like this, 1.02, and these are millimeters, so 10 to the minus 3. This is going to be squared, and it's going to be over 4. If you do that calculation, you're going to find that we have a cross-sectional area of 8.17 times 10 to the negative 7 meters squared. Okay, so that's our cross-sectional area, and at this point we just need to stick our area back into our expression for our current density. And so we're going to have J is equal to, well, I is 1.67 amps over the result we just found, 8.17 times 10 to the minus 7 meters squared. And if you do that calculation, you're going to find 2.04 times 10 to the 6 amps per meter squared. That's our current density. Okay, so that would be the answer to part A. And now if we move on to part B, we're looking for the drift speed. So in part B, the drift speed, well, we know that we can write our drift speed down, or at least we know we can relate our drift speed to our current density, which we just found through the following equation, which is just the equation from above here, right? We have it written down right here. So let's move back down here, and let's isolate our VD here. If we isolate VD, we're going to end up with an expression that looks like this. And now it's really just a matter of substituting in numbers. We need to know the charge of an electron, which we're taking the absolute value of. We're given this n value here, right? This is the free electron density in this material, right? Which is what we talked about above over here, our concentration. And so we can just substitute in those numbers. We can see that VD is going to be equal to, well, our J, which we just calculated, over 8.5 times 10 to the 28. That's our N, right? That's the density per cubic meter of these free electrons in this material. And then the charge, well, the absolute value of the charge on one electron. So I'll just write it down as positive. Right, and if you do that calculation, you're going to find that VD is equal to 1.5 times 10 to the minus 4 meters per second. So that's our drift velocity. That's the velocity that the whole column of electrons is going to be moving down this lamp wire at, right? So fairly slowly, but the lights turn on right away nonetheless, like we talked about before, because the whole column starts moving at the same time, right? Okay, so that was our first video in this series, and I will see you guys in the next one.